review on what we did last day. We introduced, well, we kind of review whenever force extension graph, there's a part where it's proportional, right? That's where it obeys Hooke's law. Then there's a little elastic limit, and then the part where it undergoes plastic deformation. We also said that when F is proportional to E, Hooke's law is obeyed, and F is equal to KE. That's okay? We also said that stress, right? The stress on an elastic medium is equal to the force acting per unit area, SI unit pascals. And then we had a next quantity called strain. That was the extension per unit length, right? Had no SI unit because it was a ratio. And then we talked about Young's modulus, right? Young's modulus which was stress over strain. Or you could have written F on A all over E on L. And as you would have seen in the little Kahoot there, right? FL all over AP. That's Young's modulus, right? And as I said, you're going to see these questions a lot in graphs, right? Right. So for example, if you see a stress versus strain graph, if you see a stress versus strain graph, then the gradient is Young's modulus. That's okay? If on the other hand, you see a force versus extension graph, right? You need to be able to rearrange this formula here and obtain whatever the gradient is. Okay? I think I did that for you. And we got F is equal to E, A on L, all by P. So the gradient was equal to E, A, all on L. All right? That's where we stopped last day. Before I move on and start past, I didn't do any past papers last day, right? I didn't finish it. I wonder why. Anyway, we need graph paper, right? So the first one, I'll probably try to see if I can do it without the graph paper. What number? It was in 2003. No, it's not it. All right. So I want to give you a small note on strain energy, and then we'll pull all this together and do some past papers, right? Right? We'll try and do at least one graph. But basically, from the graph, what is make you do is plot like stress on strain or force against extension, find the gradient, and then tell them how to get Young's modulus. All right? All right. Last heading, strain energy. For module 3. Before you draw that graph, write this, please. Consider a wire whose extension is small. Consider a wire whose extension is small when a force F is applied. When a force F is applied. Full stop. If the extension is increased, if the extension is increased by delta x, if the extension is increased by delta x, which is so small, triangle, which is so small that F is considered to be constant, then work done is given by force by the change in distance. And then work done is equal to force by change in distance. And the strain energy is equal to work done. Sketchy graph, and then I want to give you a small proof underneath. A little bit of integration, you don't have to learn it, right? I just want to show you where it came from, right? You don't have to learn to do it. Strain energy is equal to this work done. Sketch our graph quick, and then let's take a look at how to actually come up with this strain energy formula, right? Nalia, your print module 2 already. Let's stick it in there. Of course, so like, yeah, just take a picture from them now. I didn't find it, so I had to call it over. But you'll print the model 2 already. Right, so if you look at the graph there, right? If you look at the graph, strain energy, right? For those who didn't do integration, don't worry about it too much, right? But strain energy is the area under the graph. So you see that shaded area there? That shaded area represents the strain energy. And how you get the area under the graph? You integrate F with respect to X. And let's integrate between the limits X and 0. Right? I want you to note that since it obeys Hooke's law, what we can say F equal to what? If it obeys Hooke's law. And this gets X, right? Kx. Yes. Kx. So now strain energy is equal to the integral of Kx with respect to x, between x and 0. What's the integral of that? Yeah. Integral over 2. Very good. So the integral will be kx squared over 2 between x and 0. All right? So what that means is that your strain energy is equal to plug in x and plug in 0, and you'll get a half k x squared. All right? So don't worry about the integration too much, right? Just highlight that strain energy is equal to a half a squared, and is the area under force extension graph. Right? Last thing we have to look at, right? After we know what strain energy, we have to know what the graphs, the stress versus strain graph for different materials look like. All right? What the stress versus strain graph for different materials will look like, right? Should be sharing, so. Right. So we need to figure out what is graph looking like earlier, right? Exactly. Right, Nalia? How are we going to figure out what his graphs look like, right? So first thing is iron, then glass, then like rubber. and then polythene, right? So by just looking at the materials, what's the difference between iron and glass? Well, in terms of applying a force on the extension, do you expect glass to have a large extension? No, right? What about wire? Like ions, sorry. So if you had a guess, what would the graph, what would the shape of the graph look like? Well, it will have the straight line part, then the little curve and so on, right? Wire is exactly like what we did in the earlies. Okay. What about glass? Right, straight line and a little curve on the end here. Well, sorry, not curve. Huh? They, as soon as you enter the plastic region with this, that's it, right? So the real small little curve, small little curve, then it breaks. All right. So they have little or no plastic deformation. That's okay. I'm gonna draw it back again. Watch this here. So they have a straight line part, and they don't have curve like ductile materials. As soon as the hooks up and it should be, they have a slight elastic part, and that's it. A small curve. Okay, and it breaks. All right. What about rubber? Right, but in a longer plastic region. And what will happen when you release rubber? It goes back to the original, right? So rubber will carry a shape like this. When it loading, and then when it offloading, it goes right back to the original. Yeah, curve forward and it curve back in. Yeah. Right, so on top is when you load it, and underneath is when you unload it. Right, this shaded area here is a strain energy. It has a very large strain energy. And last one, PVC or plastic. How do you think it'll look? Would it go back to the original? Would it go back to the origin? No. It'll go back to some value later on, right? So it might be shaped when it load, and then when it unload, lower down. This is loading, and this is unloading. All right. So because it's polythene, it undergoes a large plastic deformation. Right, sketchy graph, take a little small note for each one, right? That's the end of the theory. Now we're gonna try some questions. All right, your answer. And they open. Lights on. Ready? Let's take this small note, right? For ductile materials, materials which can be easily lengthened, materials which can be easily lengthened, materials which can be easily lengthened, and which undergo significant plastic deformation and which undergoes significant plastic deformation. Until they break, until they break. Until they break. Next one, glass. Sorry, brittle, brittle, ductile. Brittle, brittle. Materials would break easily. Materials which break easily after reaching the elastic limit. Materials which break easily after reaching the elastic limit. Note that Dipanshu. Anyway, I'll see you there. No, that's okay. Sorry, no. Plastic. First up, plastic behavior of brittle material is almost non-existent. Plastic behavior of brittle materials is almost non-existent. You've seen that, right? Brittle, right? It has little or no plastic deformation. Huh? What is? Oh, so elastic is when you pull it, it goes back, or you apply a force and you extend it, it goes back to the original. Plastic, think of a plastic bag. You pull it, it can't go back to the original. That's plastic, right? Next one, polymeric. Azaria, listening to me? Plastic behavior, brittle materials is almost non-existent. Non-existent. No. That's brittle. I'm now going to polymer. I was just calling over for Azaria. So I was actually trying to listen in class. Good job, Azaria. Yeah, she actually listened. Next one, C, polymeric. Right? These materials depart from Hooke's law of behavior. These materials depart from Hooke's law of behavior. These materials depart from Hooke's law of behavior. For example, rubber. All right. Next one, polythene. Last one, polythene. Look at that. Polythene becomes permanently distorted. Polythene becomes permanently distorted from its original size and shape. Polythene becomes permanently distorted from its original size and shape. From its original size and shape after the applied force has been removed. And therefore exhibits plastic deformation. So that was last year. The one we did in class was this one here. We didn't do this last week? This one we did, right? Oh, Azaria, don't say yeah, it wasn't here last week. All right. Here you have some basic definitions. I can leave out that, right? Oh. No, I thought you're gonna ask me what year it is. All right, let's start here. I don't know what year it is. Just put number one. Just put number one. Let's start there, right? What stress will be required to increase the length of a material by 0.5? So they wanted to find stress on the line what they give you. All they give you there was Young's modulus and strain. Well, something like strain. Who put somebody phone? I also, oh, I don't know. I have a little phone here. How are we going to get that? Huh? That's all they give it. Young's modulus and that percentage thing. Think about it and then we're going to try to attempt it, right? Oh, look at the year here. That's 2003. What we did last was 2004. So we're going up the road. Right? So again, every time you do a question, write out what you have. All we have is Young's modulus, which is capital E, 1.2 by 10 to the 11. When you're doing questions like this, Young's modulus is normally around that range, right? 10 to the 11, 12 around there, right? So if you get minus 11, something wrong. Right, and then they told you that it increased the length by 0.15. So what's the extension? Think about it, because there's a way for you to figure out the strain, right? If you figure out the strain, then we could use a formula and find stress, right? By the way, what is 0.15%? Right, so it's like, no, it's not 15. Yeah, 1% is 1 in 100. So 0.15% is 0.15 over 100. Okay? So let's think about it and then I'll help you out. There must be a way for you to get strain. What's the formula you think you can use here, Shivish? What formula do you think you can use here? You're seeing stress there, you're seeing strain there, and you're seeing Young's modulus. If you had to put it all together, what formula you think you might have to use here? Correct, Azaria. Yeah. What you would use? I'll give you a little summary before, so check. Which one there you might use? Huh? No, if you figure out strain, what's the formula you think you might use? Young's modulus is what? Stress over strain. Right, so stress is Young's modulus by strain. But we need to figure out strain. How do you find strain again, Nikash? Strain is what? Extension over length, right? What's the extension of the original length, right? So 0.15 over 100 of the original length. And the original length is what? L? Or them to the L's. So therefore, strain energy is really, strain is 0.15 over 100. You listening? Right? Remember, the extension is how much the length of the wire increased by, right? And the length of the wire increased by 0.15 over 100 of whatever the original length was. right? So you don't need to know the original length because they'll cancel off nicely, right? So the L's will cancel and you'll end up with that. You'll get it. How much? 1.8 by 10 to the 8 pascals, right? The next part one time, yeah, sorry. Because what is extension? Extension in this case is 0.15% of L, right? Of the length. Divided by the length. Do the next part now, please. Huh? I know what's been. What you get for your next part? Right, they gave us the area, calculate tension. What's the formula we're using now, Aaron? What we're using now to get tension. And they gave us the area. Tension, yeah. Tension needed. What we gonna use now? Remember, we just found stress, right? So which formula are you going to use to help find tension? Tension is a what? Tension is a force, right? Huh? FL over A. E. All right, but why does we use stress equal to F1A? Right, but that can work too, but I will take it a little bit longer. But we could just use stress is equal to force over area. All right, and then solve. But we have a slight problem there. Area is in what Nalia? No, sorry. Michaela. Millimeter squared. It has to be in what? Meter squared. How you convert millimeter squared to meter squared? You divide by 1,000 twice, right? Right? Yeah, you divide by 1,000,000. Well, you divide by 10 to the 6. Or you write 10 to the minus 6. Yeah. Huh? Yeah, 1,000 squared. Right? And then solve for the force, right? So that's 1.8 by 10 to the 8 by the area, which is 2 by 10 to the minus 6. Anybody got us? 3.6 by 10 to the 2. No? Yeah. All right, next part. Calculate the work done if the wire is 1 meter long. Calculate the work done if the wire is, yeah. That can, yeah. I just work it out from my head there, so that's why I didn't write it down. So that could work. Last part. Calculate the work done if the wire is 1 meter long. Very good. Strain energy. So you're finding the strain energy. Malia, just come on, sit down here. You got a graph paper? How much people need graph paper? Need? Nah. I can also work with graph paper. That's too much. I can't give all the graph paper. I'll skip out that one. I'll skip out the graph paper question. Shavish, are you done? Right, online you can send all the answers there. Alina, Alexa, you can send all the answers there. Right, so work done basically means strain energy. So that'll be a half kx squared. Do we have k? Do we have k? Ranju, do we have k? No. So can I write this formula a different way? Remember, f is equal to kx, right? Yeah. I mean, we know what f is. F is tension. So we can write it as a half fx. You'll figure it out now. Nilia, work out Nilia support. Where are you? Are you working it out? F is how much area? So that's 360, right? And x is how much? Yeah. What's x? What's the extension? Right? The extension is 0.15 over 100 of the length, which is 1. Right? The length is 1, right? So it's 0.15 over 100 of 1 meter. However you want to write it. What's that? How much y'all got in joules? Point 0.27. Ishmael, all again, should there? Shania. Are you ready? I will stick in my head now. All right, let's go again. Are you okay there? Everybody okay there? Nalia. No, next side was I phone there? Oh. Let's go again. Oh gosh. All right. This one here, they wanted to draw the graph for glass and rubber. That's 2008. Right? But forget that, right? Because you're not to do that, right? Yeah. Let's go here. Let's do the hard part. Let's do my favor now. Write down all the info. Write down all the info here. Pardon me, ma'am? Yes, ma'am. No, ma'am. It's now till 8:30, ma'am. Class is still 2. Same price, but it's still 2 hours now. It's always been 2 hours. After this one, you'll get a break here. Nalia, you can just come and sit down right here, you know. Oh. I got my eyes on you. Right, hurry up. Let's try this one here. Nikolai, how far I reach? Pardon me, this 2008. Number. Eight, 10 to the power 8. I got my eyes on you. Serious? And it's a whole song? Hey, don't worry, we have the question right here. We can work it out fast. All right, so write down all the information. You'll recognize that what happened here. What they did here is they include circular motion in Young's modular question. So you have to remember your circular motion. The first part is show the forces acting on the mass. Drawing diagram earlier. What are the forces acting on this mass? Divish. Hurry up, Divish. What are the forces acting on this mass? What are the forces acting on the mass? Tension acting in what direction? Towards this right, towards this equilibrium point, and what else? And weight acting downwards. Quick question. I'm moving in a circle, right? So what is the resultant of those two forces called? centripetal force. And centripetal force always acts towards the water layer, toward the center. So tension minus weight. Okay? So part 1 is to draw the forces. Part 2, at the lowest point, find tension. Then stress, extension, and so on. Right? So listen again what they asked for, right? Question asked at the lowest point. Part A, find tension. Part B, find the stress. And part C, find the extension. Pardon me? What's the constant value for? Oh, what I did 9.8. 9.81. Sorry, sir. 9.81. You'll get 0.01 more marks on the exam. Hurry up. Try that in. Let's see where you get there, then I'll give you 5 minutes and then we continue. Yeah. Right, so I gave you the information needed there, right? So tension is what? You got everything there. Tension is what? Right? Centripetal force plus the weight, right? Could we find the weight? Yeah. Problem is finding. Right. So take a look at the quantities they gave you. They gave you velocity. See if that can help, you know. So yeah, check and see what formula you will use to find centripetal force. Check and see which one you will use, right? Well, the exam is a little later now, it's 20 something, yeah? When is unit 1? Huh? Which T? No, T is tension yet. That's the period. Very good. MV squared on R. Because you have radius. Radius is 1, right? That T is talking about the period. So you're not doing that. This T is tension. Right? So yes, centripetal force MV squared on R. MV squared on R. I see, I remember your centripetal force formulas, right? Okay, find stress. Right, force on area, and you found the force there. Area is what? All right, so part A, tension is centripetal force plus weight. So that's mv squared on r plus mg. Yeah, 1. What was the mass? 0.5 by 38 squared plus 0.5 by 9.81. Push-ups. All over, r is 1. Anybody have an answer? How much? 727 or 747? Nice. Now let's have tension, find stress. Find your stress, then find your tension. No, but we had to find it. And they gave it diameter of the wire. Pi r squared. Right, so stress is force over area. The force in this case is tension. And the area is pi by r squared. And they gave us, oh no, sorry. What they gave you there? Diameter, right? So don't forget to divide by 2. So what? It's already in meters. Yeah, listen. Huh? No, well, you had a half to the diameter. Because the one is the radius of the circular part. Huh? Right, okay. You okay with the first R? Right, the first R represents the radius of the circular part. Right. The next R is pi r squared to find the area of the wire. The cross-sectional area of the wire. Right? So to use that R, you're using this value here, 2 by 10 to the minus 3. And then multiply by pi and divide 2.31 by 10 to the 8th. Anybody else got a 2.31 by 10 to the 8th? Nice. Online, you're okay, right? Alina? Shania? And again, the answer tomorrow. I want to make sure all you okay. All you okay, right? All right. Do the last part, the extension, then I'll give you 5 minutes. What's up your brain in a hard one? Oh, sorry. Who said that? Yeah. And that's the original line to the wire. What's the formula we used to find extension? Using Young's modulus. Correct. Young's modulus. Look at, and one more thing I want you all to see. So far, we use the mass, we use the length of the wire, we use the diameter, we use the speed, and we use the breaking. Oh, we use the breaking stress at one more part. And then, so now it boils down to using the Young's modulus, right? You also saw the value there for the breaking stress. 7.2 by 10 to the 8, right? So based on what happening here, will our wire break? Will our wire break? No, because the value is smaller. Okay? But if it somehow becomes more than 7.2, right? Oh, good. That's a good question, Nalia. What will make the breaking stress become more than 7.2? What is one of the factors here that can make it break, make the wire break? Look at it there. What's one of the things there that we could change and make the wire break? Okay, mass is one. What else? The velocity. That's all looking for, the velocity. Right? You can make it move faster. All right, that's now. All right, so last part we're using Young's modulus is stress over strain. Right? You can do it like this, or here's what, right? Since we have all the quantities already, we can use E is equal to FL over AE. Right? And just make E the subject of the formula, FL over A by capital E. F is 727. The length of the wire is 1. The area was pi r squared, whatever that was. And Young's modulus was 2 by 10 to the 11. And it should get 1.155 by 10 to the minus 2. That's okay? Right? You should always be aware of your answers, right? If by chance you got something bigger than 1, it means there's something wrong, right? Trouble area? Trouble? For which one? Yeah, the length is 1. The wire has a length of 1. We worked out the force, we know the area, and we're trying to find the extension. Right? Yeah, the last part. So long? All right, yeah. Copy it down, take a little break till 8 o'clock, right? And then let's take a look at the hard one. You all do have graph paper, so I can't give another these graphs.
is you. She's singing for Drake and Kanye. What's your reaction? Kanye, right? What's Drake on? Are you ready? I can listen to you.
Anybody could while you wait, right? Anybody could send me 2015 soft copy. If we get 2015, send it for me now. Last one here, 2015. Right, hurry up. I want you this fast, please. Right, if you check in the group, you'll see it, right? 2015. Number 6, trying to do the whole thing, right? Numbers. Okay, by definition, same thing is the ratio of stress on strain. So which one are asking for? F, L, T, or stress on strain, and that's defined. It's doing 3 marks in it. I don't know why they gave some lines, but it's just 3 marks. All right, next part. Explain that fast. Elastic deformation. We can see that this stress is proportional. Yeah, all right, yeah, and make sure you mention that it goes back to the original extension, original length. Sorry. All right. For inelastic, I want to write this one down. Right. Inelastic deformation occurs inelastic. Inelastic deformation occurs when an object goes beyond its elastic limit. And it is permanently deformed. And it is permanently deformed. Yeah, yes. But in terms of energy, write this down. First up, its elastic potential energy. Its elastic potential energy is converted into other forms of energy. For example, heat, kinetic, or sound. For example, heat, kinetic, or sound. Look at that. But in elastic deformation, it doesn't exceed the elastic limit, and its potential energy stays the same. That's okay? But in inelastic, the elastic potential energy is converted to something else. Okay? All right, this is the first calculation, part C. Part C here. Azaria, no, there still. Sivalina, there still now, please. All right, so again, do the usual thing. As you read the question, underline all the important stuff, right? Young's modulus, under compression, they give you the stress. Assuming that the femur is so long, calculate the amount of compression it can withstand before breaking. Work in millimeters. Or leave your answer in millimeters. What are they asking you for there? Amount of compression. What are they asking you for? Now you'll be more specific. The extension. Well, compression in this case, right? Compression is the reverse of extension. That's okay? You want? See what quantities you have now. Try to work it out. Online, please. Please message an answer. Just one answer for the class, please. Anybody online besides Tavisha. Ready? All done? Hello? I'll get you here. So they want you to get Young's. They want you to get these things here, right? So we could use Young's modulus is equal to stress over strain. So it means that strain is equal to stress over Young's modulus. Stress is equal to 1.5 by 10 to the 8. Young's modulus is 1.8 by 10 to the 10. Okay? That'll give you a strain, right? But remember, strain, we don't want strain, we really want extension or compression, right? Strain is extension over length by 1.5 by 10 to the 8 over. That's okay? And remember, we already know what L is, right? L is 0.47. So the extension is 1.5 by 10 to the 8 all over 1.8 by 10 to the 10 by by 10 to the minus. Right, so that'll be meters, and then you multiply and you'll get 3.92, you said? So 3.92 millimeters. That's the amount of compression that the bone could handle. Most handles will be close to the real values here. All right, and now for the hard part. Yeah, videos already. You know reach? You know reach or? You know reach or? I'm gonna slow it. The longer in a way. Well, it have other conditions to look at, but based on this here. Right? So figure 6 shows a crane, right? And that's the time. Let me see how far we can reach with it now. I think one of the parts was tricky. I can't remember the first or the second part. Right? So they give you a crane, I had a cable, and it lifting an object of mass 1,800 kilograms. It has a motor, ground, and so on, right? The motor on the crane lifts a total mass of 1,800 kilograms from rest to the ground. The cable supporting the mass has, so they gave us a mass here. They gave us a Young's modulus. The cross-sectional area is 1.3. As the mass leaves the ground, they give it a strain. Use the Young's modulus to find tension. Could we handle that? Try that fast. Shouldn't be too difficult. Kinda, yeah. So what's the formula we're starting with here? No. Centripetal force only used when it has circular motion. So it do have circular motion here. Huh? How? Yeah, well, you have to find for the force here. Tension is the force. Right, later on, yeah. Right, but you will need to get actually you gotta go and do all that. Young's modulus is what? Stress on strain. Right? You already know what strain is, right? So it means that stress is the Young's modulus by the strain. Right? But stress is really what? In this case, tension over area. And they give you the area. So that's it. Tension is equal to Young's modulus by strain by area. All right. Let's just talk to the last part because I wanted that to finish out the whole thing after. Or the last part here. Assuming it is a 8-ton crane. Tension over here, yes. So just find the stress and then find for what you need. Assuming it is an 8-ton crane and the length of the cable is 8 meters, determine the extension when operating the load. What you would do? What you would do here? We know this strain, right? How you'd work out the extension? Strain is extension over length. Do we have the original length? No, we don't have the original length. So how we'll do that last part? Shania, you with us still? Sorry? Yeah, and the length of the queue, 8 meters, yeah. L is 8. L is 8. All right, this wasn't the hard question. It was the one later one. Now, I'll do a revision on module 3 next week, and then we start module 2. All right, super homework, finish it up, right? Finish it up for homework, and then you can try the one in 2000, I think it's 2017. All right. All right, online. So that's it for today.